It's most helpful if before you do this lesson, you've gotten some practice with definite integrals. Assuming that you've gotten some practice and that you're getting better at working with definite integrals, we're going to move on to finding the definite integral of an absolute value. Remember that the derivative at a vertex of an absolute value does not exist. So when we evaluate the integral from 0 to 2 of 2x minus 1 dx, knowing what that graph looks like will be helpful in determining whether or not we're going to have a vertex be part of our problem. So we'll have 1, 2, 3, 4. Actually, let me see if I can make this. I'm going to try and make this a little bit bigger. We're going to make this 1, 2, 3. So when we put a 0 into the absolute value of 2x minus 1, we're going to get a 1 out. And when we put a 1 in, we're going to get a 1 out. So what's happening in between? When we put a 1/2 in is when we get a 0 out. When we put a 2 in, we're going to get a 3 out. 1, 2, 3. So you can see we've got the right part of our absolute value, and then we've got the left part of the absolute value, and we are evaluating from x equals 0 to x equals 2. And smack dab in the middle of our limits of integration, our lower limit and our upper limit, we have a problem. We have a problem because we can't find the antiderivative if we have a point in between that range of limits from 0 to 2, if we have a point where we can't find the antiderivative because the derivative doesn't exist. Therefore, we're going to have to cut this up into 2 parts. Now remember, this was 1/2. So think of this as your A, your B, and look at that. C is right between A and B. So we're going to break this integral up into 2 parts, 0 to 1/2 plus 1/2 to 2. Now, we can't just take the absolute value of 2x minus 1. We have to look at what this curve is a straight line. It's a linear part. So its linear equation is the opposite of 2x minus 1. If you were to take the opposite of 2x minus 1, you would have negative 2x plus 1, and you can see very clearly we have a y-intercept at 1, and then we have a slope of negative 2. And then we're going to have this straight line, which is a linear line, which has an equation of 2x minus 1. So from 1/2 to 2 on the x-axis, we're looking at the curve being 2x minus 1. And from 0 to 1/2, we're looking at the curve being the opposite of 2x minus 1. So this definite integral is going to be, I'm going to take that negative to the outside, which I can. Or I can distribute the negative. I can think of it as negative 2x plus 1. It's going to be negative x squared, not over 2, because the 2's we need that to be a negative 2x. So the opposite of x squared plus x evaluated from 0 to 1/2 plus, then we have this part right here, positive x squared, the antiderivative of 2x is x squared, minus x evaluated from 1/2 to 2. And the green part, when I put a 1/2 in, I'm going to have negative 1/4 plus 1/2 minus, right, that's when we put 1/2 in, minus 0 plus 0. And then we're going to add to that our second definite integral. When we put a 2 in, we're going to have 2 squared minus 2 minus 1/2 squared is 1/4 minus 1/2. Lots of fractions here. Negative 1/4 plus 1/2 is 1/4 minus 0 plus 4 minus 2 is 2 minus negative 1/4 so we have 1/4 plus 2 plus 1/4, which is 2.5, which is 5/2. Okay, here's one for you to try. Now you may need to do this on another piece of paper if you've used a lot of the paper that was already there for you. I'm going to show my work as I go. And I got 2 integrals. Oh, gonna do this silently so that you can work. The opposite of x minus 2 dx plus the integral from 2 to 5 of x minus 2 dx. So okay, hopefully I slowed up a little bit at the end there so that it gave you some time to work it out on your own. And you should see the answer. Hopefully that's what you got. And in our next video, we're going to talk about applying this to marginal analysis.